Allie, and this is Lawrence, and welcome to our YouTube channel, Physics for Dummies.
Yes, the real name of the channel should be Physics for and by Dummies. Today we are going to discuss the physics behind the classic game of Jenga.
This is the perfect topic for Lawrence because his life is falling apart like a Jenga tower.
Well, you're not wrong there, but let's move on to the actual physics.
A little bit about the setup of Jenga. It's made up of 54 wooden blocks stacked in a tower that is 18 levels high with 3 blocks in each level.
Lawrence is going to use a spring scale to measure the weight of a small cup. He will then add a single Jenga block to that small cup and measure the weight of them together. Next, Lawrence will measure the weight of a wrench, which will be placed on top of the block when they are slid across the table using a spring scale. Lawrence will now slide the block and the wrench across a platform of other Jenga blocks using a spring scale at a constant velocity. Lawrence will then repeat the same process, except now sliding the block and wrench across the table using the spring scale, which should produce a different coefficient of friction. Now we are going to calculate the coefficients of friction. Here we have the weights and the forces of pull Lawrence found using the spring scales. Next, we found the weight of the Jenga block alone and added it to the weight of the wrench. We used this force of weight to calculate the mass of the system of the wrench and the Jenga block. We know that the force of weight is equal to the normal force because the system is not accelerating in the y direction. We will now calculate our friction coefficients. We sum the forces in the x direction, knowing that the acceleration is 0 because we pulled the spring scale at a constant velocity. We calculate our force of friction and plug it into the equation force of friction stack max equals mu sub s times the normal force to get our coefficient of friction. We repeat the same process, except now we have a higher mu when we pull the block over the platform of blocks.
The blocks on the bottom experience a greater force of compression because of the weight on top of them. Therefore, they should be hard to pull out, as seen by the tower shaking and rotating.
There are also blocks throughout the tower which are very easy to pull out. These blocks do not support a lot of load. This is because no two Jenga blocks are made exactly the same and rest on each other unevenly, making some blocks easier to pull out than others. The easiest way to make a Jenga tower fall is to remove the 2 bottommost side blocks. This leaves the tower supported by only the middle block and magnifies each motion when a block is pulled from the tower. This makes the tower more likely to fall now that it is only supported by the middle block.
Our conclusion was not very conclusive at all. We found there's no surefire way to win at Jenga. This is because no block or tower is exactly the same as another. We can, however, offer tips to win at Jenga more often. Our first tip is to look for blocks that are already loose. These blocks should have a lower mu and carry less of a load and therefore should be easier to pull out. Our second tip is to never remove the bottommost side blocks. As demonstrated, this makes the tower fall over a lot quicker. Our third and final tip is to avoid bottom blocks if possible. As shown, these are under greater forces of compression and should be harder to pull out. Thank you for watching, and don't forget to subscribe to Physics for Dummies. We make new videos never.
Hi, and welcome to our YouTube channel, Jenga.
What?
I said Jenga.
This is a great channel, it's Jenga. I love the channel Jenga. All we do is Jenga stuff.
Okay, retry.
I don't even want to do this anymore.
Red!
The dog shoot.
Hi, buddy.
You know, he should replace me. He obviously knows what he's doing.
What, Lawrence? The dog should replace you?
Yes.
Now that the Jenga tower is only supported by one...
You made it fall too fast.
I'm sorry!